Greetings! This is the fifth lecture on the Riesz representation theorem. Here is a reminder of the statement. On a locally compact Hausdorff space x tau, we are given a positive linear functional lambda defined on CC of x. Our goal is to represent this functional lambda by a Borel measure mu, in the sense that lambda of f equals the mu integral of f for all f in CC of x. We, moreover, claim that the measure mu satisfies the regularity properties A to C. The measure of every compact set is finite, and the measure of every measurable set E can be approximated from above by the measures of open sets, and from below by the measures of compact sets, except that the approximation from below is only guaranteed under the additional assumption that the measure of E is finite to begin with, or alternatively assuming that E is an open set, but may in this case have infinite measure. We also claimed that the measure mu satisfying all these properties is unique, and this we already established 2 lectures ago. On the previous lecture we had time to define the sigma algebra F and the measure mu and start verifying the properties of mu. We will surely recall the definitions of F and mu during this lecture, but we'll save the effort to where we really need it. Here is just a quick reminder of the properties we already had time to prove last lecture, and which will also be needed on this one. First, we have initially defined the values of the set function mu on the full sigma algebra P of x, and we have shown that this set function is an outer measure. In other words, it is monotone and countably subadditive on all subsets of x, and assigns the value 0 to the empty set. However, mu is typically not countably additive on the full sigma algebra, so mu is not a measure on P of x. Then we also showed the following formula for the mu measure of a compact set K. Mu of K equals the infimum of the values lambda f, where f ranges over all functions dominating K. This equation was a fairly simple consequence of Urysohn's lemma and of course the definition of mu. Finally, we pointed out, relying on this formula, that the set families F and F0, defined on the previous lecture, contain all the compact sets. That was a brief recap of what has happened before, and now we start to pursue new topics. The first one will be the inner regularity of open sets. Here is a reminder of what this means. If U is an open set, then the mu measure of U is the supremum of the mu measures of compact sets K contained in U. This formula implies, by the way, that the set family F0 defined on the previous lecture contains all the open sets with finite mu measure. Indeed, by definition, F0 consists of all sets with finite measure, which are inner regular in the sense we just explained. Let's then prove the inner regularity of open sets. Fix an open set U and a real number alpha, which is strictly smaller than mu of U. If mu of U is 0, this parameter alpha might even be negative. Now, by definition, mu of U equals the supremum of the values lambda f, where f ranges over the functions dominated by U. It follows that we may find and fix some continuous function f, which is dominated by U, and such that alpha is smaller than lambda f. Let's write K for the compact support of f. Now it suffices to show that lambda f is no larger than mu of K. This will show that the measure of the compact set K, which is contained in U, is between the parameter alpha and the mu measure of U. This will complete the proof of the inner regularity formula for U. To prove the inequality lambda f is less than mu of K, let's fix an arbitrary open set V which contains K. Then f is dominated by V, so lambda f is no larger than mu of V, by the definition of mu on open sets. But here V was an arbitrary open set containing K, so we may deduce that lambda f is smaller than the infimum of the mu measures of open sets V containing K. This infimum equals mu of k by definition, and we have proved the inequality we claimed. The next goal will be to show that the set function mu is countably additive on the family f0. This does not quite mean that mu is a measure on f0, since f0 is not a sigma algebra, but we are getting pretty close. The precise claim here is that if a1, a2 and so on are members of f0, which are disjoint, and A is their union, then the mu measure of A equals the sum of the mu measures of the sets AI. We can't always guarantee that A would be an element of f0, since f0 only contains sets of finite measure. However, we can prove the best possible thing, namely that if the mu measure of A is finite, then it lies in f0. We start the proof by handling a special case where there are only two of the sets and they are both compact. So fix two disjoint compact sets K1 and K2. We claim that the mu measure of their union equals the sum of their mu measures. Using the Hausdorff axiom and the compactness of the sets K1 and K2, it is easy to find an open set U which contains K1 but is disjoint from K2. We proved something very similar in lemma 2.6, and this claim follows essentially by the same argument. Now we use Urysohn's lemma to find the function f, which dominates K1 and is dominated by U. Since U doesn't intersect K2, in particular the function f is identically 0 on the set K2. Now forget about the function f for a moment, and note that the union of K1 and K2 is also a compact set. So its mu measure is given by the formula we established on the previous lecture. The mu measure of K1 union K2 equals the infimum of the values lambda g, where g ranges over all functions dominating the union of K1 and K2. By this formula, we may find a function g which dominates the union of K1 and K2, and such that lambda of g is no larger than mu of K1 union K2 plus epsilon. Here epsilon is any positive number. Now we have two functions f and g, where f dominates K1, g dominates the union of K1 and K2, and f moreover vanishes on K2. Therefore, K1 is dominated by f times g, and K2 is dominated by 1 minus f times g. With these facts in hand, we may estimate as follows. First, the sum of mu K1 and mu K2 is bounded from above by lambda of f times g plus lambda of 1 minus f times g, which we have written out as g minus f times g. This inequality uses the two dominations mentioned above, and of course also the formula for the mu measures of compact sets from the previous lecture. Now we may use the linearity of lambda to conclude that the previous sum equals lambda of g. And here g was chosen so that lambda of g is no larger than the mu measure of K1 union K2 plus epsilon. Letting epsilon tend to 0 shows that the mu measure of K1 plus the mu measure of K2 is bounded from above by the mu measure of K1 union K2. The converse inequality follows simply by the subadditivity of mu. Now we have established the finite additivity of mu on compact sets. Of course, if you have any finite number of disjoint compact sets, then you can now use induction to show that the mu measure of their union equals the sum of the mu measures. Next, we consider the case of general sets. Let AI be a countable family of disjoint elements of F0. We claim that the mu measure of their union equals the sum of their mu measures. Now we get to use the definition of the family F0. All the sets AI have finite mu measure, and we may find compact subsets Ki whose mu measures are no smaller than mu ai minus epsilon divided by 2 to the power I. Since the sets ai are disjoint, also their compact subsets ki are disjoint. We are then in a position to use the special case we proved before. Recall that A is the union of the sets ai. First, by monotonicity, the mu measure of A is no smaller than the mu measure of the finite union of the sets k1 through to kn, where n is an arbitrary natural number. Then, by the special case for compact sets, this measure equals the sum of the mu measures of the compact sets ki, where I runs from 1 to n. Now the compact sets ki were selected so that this sum is no smaller than the corresponding sum of the mu measures of the sets ai minus an epsilon. With this inequality in hand, we may first let n tend to infinity and then epsilon tend to 0 to see that the mu measure of A is no smaller than the sum of the mu measures of the sets ai. The converse inequality follows once more by subadditivity and doesn't need the assumption that the sets ai are elements of F0. Apropos that, we had also claimed at the start of this section that if the union A has finite mu measure, then it lies in the collection F0. To show this, we have to make sure that the mu measure of the set A can be approximated from below by the mu measures of compact subsets of A. This follows easily from the inequalities we established in the course of the previous proof. Namely, the mu measure of A is greater than the mu measure of the union of the compact sets k1 through to kn, where n is arbitrary. Of course, this union here is a compact subset of A. Moreover, the mu measure of this union is no smaller than the sum of the mu measures of the sets ai with indices between 1 and n minus epsilon. Now, if you let n tend to infinity and epsilon tend to 0 on the right-hand side, you will find the full sum of the measures of the sets ai. This full sum is at least as large as the mu measure of A by subadditivity. Actually, we know by now that this full sum is precisely the same as the mu measure of A. This means that already with a finite n and a positive epsilon, you can get as close to the mu measure of A as you like. And then the mu measure of the union of the sets ki for indices between 1 and n is an even larger quantity. This proves the inner regularity of A by compact sets and shows that A lies in F0. The title of the next fairly short section is Inner and Outer Regularity of Sets in F0. You might wonder what this can mean. Don't we already know both properties? Well, yes we do, but in this section we establish a variant of these properties which, at least superficially, looks a little stronger. Namely, we claim that if A is a member of F0 and epsilon is a positive number, then we can find a compact subset K of A and an open set U containing A such that the mu measure of the difference set between U and K is no larger than epsilon. It might be a good idea to stop the video now and ask yourself, why is this fact at least as strong as the inner and outer regularity combined? Let's prove the claim. First, by the definition of mu, there exists an open set U containing A such that the mu measure of U is smaller than the mu measure of A plus epsilon over 2. In particular, since A is a set from F0, its mu measure is finite, and so is the mu measure of U. Next, by the assumption that A is a member of F0, there exists a compact subset K whose mu measure is no smaller than mu of A minus epsilon over 2. Now we claim that K and U are the sets we want. That is, the mu measure of the difference set is no larger than epsilon. To see this, first note that the difference set of U and K is open and has finite mu measure. So it is an element of F0. In particular, we may apply the additivity of mu on F0 to the difference set. We also want to use the additivity to the compact set K, so we need to remember from the previous lecture that F0 contains the compact sets. With these remarks in mind, we see that the sum of mu of K and mu of U set minus K equals the mu measure of U. But this quantity is smaller than mu of A plus epsilon over 2, which was finally no larger than mu of K plus epsilon. Now we can subtract the finite number mu of K from both sides to obtain that the mu measure of the difference set of U and K is smaller than epsilon. This is what we claimed. Next, we come to one of the main claims of the theorem. The family F is indeed a sigma algebra, and it contains all the Borel sets. Note that this is a claim about F, not F0. We will recall the definition of F in due time, but first we still prove a few intermediate properties regarding F0. Namely, we claim that if A1 and A2 are sets in F0, then also their difference set, intersection, and union lies in F0. We start with the difference set. It turns out that the claims about intersections and unions then follow as corollaries. Let A1 and A2 be members of F0 and fix a positive parameter epsilon. To show that the difference between A1 and A2 lies in F0, we need to verify the inner regularity of this difference by compact sets. By the previous section, we can find compact sets Ki inside Ai and open sets Ui containing Ai, such that the differences of Ui and Ki have mu measures less than epsilon. Then we make a little set theoretic observation. First, the difference set of A1 and A2 is obviously contained in the difference set of U1 and K2, since U1 contained A1 and K2 was contained in A2. Next, we observe that this latter difference set is contained in the union of three difference sets: the differences between U1 and K1, K1 and U2, and finally U2 and K2. You may want to press pause here to get convinced. If you believe these inclusions, then by monotonicity, and from the way the sets Ki and Ui were chosen, we see that the mu measure of the difference set between A1 and A2 is no larger than 2 times epsilon plus the mu measure of the difference set between K1 and U2. But now the difference between K1 and U2 is a compact subset of the difference A1 set minus A2 of nearly the same mu measure. This implies that the difference between A1 and A2 lies in F0, as we claimed. Next, let's have a look at the union of A1 and A2. The union can now be rewritten as the disjoint union of two elements of F0, namely the difference between A1 and A2 and A2. But we showed in the previous section that F0 is closed under disjoint unions, at least if the measure of the union stays finite, and this is obvious if there are only finitely many sets in question. So the union of A1 and A2 lies in F0. Finally, the proof regarding intersections is even easier. The intersection between A1 and A2 can be rewritten as the difference between A1 and the difference of A1 and A2. Both sets appearing in this difference lie in F0, so the intersection of A1 and A2 lies in F0. We then move on to the real deal, showing that the family F is a sigma algebra containing the Borel sets. Here is the definition of F. It consisted of those subsets A of x whose intersection with every compact subset K of x lies in the family F0. We then start verifying that F is a sigma algebra. First, the whole space X lies in F, because the intersection of X with a compact set K is just K itself, and we know that F0 contains all the compact sets. Next, let's show that F contains complements. Fix a set A from F and a compact set K. Then the intersection between the complement of A and K can be rewritten as the difference set between K and the intersection of A and K. Both of these sets lie in F0, using the assumption that A was chosen from F. Since F0 was closed under taking differences, we see that this difference set is also a member of F0. Since the compact set K was arbitrary, we have now proven that the complement of A is a member of F. Next, we claim that F is closed under countable unions. Let A1, A2 and so on be sets from F and write A for their union. Fix also a compact set K. We need to show that the intersection of A and K lies in F0. To this end, we define inductively a sequence of sets Bn. First, B1 is simply the intersection between A1 and K. For indices n, which are at least 2, we then define Bn to be the intersection between An and K, but then we still remove the union of the sets Bj with indices j between 1 and n-1. It's now easy to check by induction that the sets Bn are elements of F0, using again the fact that F0 is closed under taking differences and finite unions. Moreover, the sets Bn are disjoint, and their union is the intersection between A and K, which is evidently a set of finite mu measure. We have shown before that F0 is closed under taking disjoint unions. So we may deduce from this equation that the intersection between A and K lies in F0. This is what we claimed, and we have now shown that F is a sigma algebra. Finally, it remains to check that F contains the Borel sets. Since the Borel sets are the smallest sigma algebra containing the closed sets, it's enough to show that F also contains the closed sets. But this is clear. If C is a closed set, then the intersection between C and any compact set K is again a compact set, and hence lies in F0. This means that C itself lies in F. We have now shown that F is a sigma algebra containing the Borel sets. It's also good to keep in mind some of the steps in the proof above, in particular that F0 is closed under taking finite unions, intersections and differences. We are now almost done with checking the properties of the measure mu. This might already seem a bit repetitive, but in the next section we check the inner regularity property C. This property stated that if A is either a set from F with finite mu measure, or then A is an open set, then the mu measure of A can be expressed as the supremum of mu measures of compact subsets of A. We already showed this if A is an open set as the first topic on this lecture. So it remains to consider a set A from F with finite mu measure. Recall that the set family F0 was defined so that this kind of inner regularity holds for all elements of F0. So, to prove our claim about sets in F, it suffices to prove the following equation. F0 consists of precisely those elements of F with finite mu measure. The forward inclusion is simple. Fix a set A from F0. Then A has finite mu measure by the definition of F0. To show that A also lies in F, we need to show that the intersection of A with any compact set K lies in F0. If K is compact, then we have seen before that K lies in F0. We have also showed that F0 is closed under finite intersections. Therefore, the intersection of A and K lies in F0 as we wanted, and hence A lies in F. Let's then prove the less trivial backward inclusion, where we fix a set A from F with finite mu measure. We claim that this set A lies in F0. What needs to be done by the definition of f0 is to find a compact subset K of A whose measure is arbitrarily close to the measure of A. In other words, the measure of A should be bounded from above by the measure of K plus epsilon. To find such a set K, we start by selecting any open set U which contains A and has finite mu measure. Such a choice is possible because we assume that A has finite mu measure. Then U is an element of f0. It now follows easily from the definition of f0 that we can find a compact set H which is contained in U and such that the mu measure of the difference between U and H is smaller than epsilon over 2. To be precise, this is a bit stronger than the definition of f0 and also uses the additivity of mu on elements of f0. We have already seen a similar argument earlier on this lecture. Next, recall that A was an element of F, so its intersection with the compact set H is an element of f0 by the definition of F. This means, again by the definition of f0, that there is a further compact set K which is contained in the intersection between A and H, and such that the mu measure of this intersection is no larger than the mu measure of K plus epsilon over 2. Finally, we get from the subadditivity that the mu measure of A is bounded from above by the sum of the mu measures of the intersection of A and H and the difference set between A and H. But since A was contained in U, the second term can be further bounded by the mu measure of the difference between U and H. Now we can combine the estimates we obtained earlier for the two terms on the right hand side. They are bounded by mu of K plus epsilon over 2 and epsilon over 2 respectively. We have now found the compact subset K of A which approximates the mu measure of A, and this shows that A is a member of f0. The proof of property C is now complete. As the last point on this lecture, we just combine some of the claims we have already established before to verify that mu is indeed a measure on the sigma algebra F. After this short section, the only remaining point will be to establish the relationship between lambda and mu, but we will leave this climax for the final lecture. To verify the fact that mu is a measure on F, first note that F was already shown to be a sigma algebra, so the claim makes sense. We have also noted earlier that mu assigns the value 0 to the open set. This can be seen in several ways. For example, the 0 function dominates the compact empty set, and lambda of 0 is 0 by linearity. How about the countable additivity of mu on the sigma algebra F? We already proved earlier on this lecture that mu is countably additive on f0. Then the corresponding claim about F follows from the relation we proved in the previous section, namely that every finite measure set in F also lies in f0. This is strong enough to give countable additivity on F, since countable additivity becomes trivial if any of the sets under consideration has infinite measure. We have now established all the measure theoretic claims in the Riesz representation theorem. The relation between lambda and mu is not too difficult to prove, but we save this for the next lecture. Goodbye for now.